Hello and welcome back to Calculus 1, section 4.5 on optimization problems, or should I say the crash course in, how to make money with calculus. So this is another section where 100% of your problems are word problems, which means this is something you really pay attention to because this is a money-making section. All sections prior to this one were, yeah, okay, fine, calculus, blah, 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 right? But now we are doing, again, applications, which means that you can make money with this. Now, also, in addition to figuring out min and max, which is what optimization is, you're also looking for functions that model the situation, which is where you actually make money in the field. Being able to predict or describe a situation mathematically, predict the outcomes, or compute the outcomes, better to say that way. All right, so now let's start with first to explain what optimization is. So we're constantly interested in optimizing something, meaning what is the maximum, what is the minimum, right? You want to maximize the profit, minimize the cost, and they go hand in hand, right? When you are running a business, and the way we do this is very systematic. You will have two functions. You plug one into another. You take the derivative, which will be equal to 0, and you already guessed it from there, right? If the derivative is equal to 0, that means that you have your extreme point, which optimizes the concept. Now let's start with a very basic, boring problem. The sum of two numbers is, let's say, I don't know, 18, whatever. Let's go 16, it's a little bit smaller. Small of the numbers is 16. Find the two numbers such that their product is maximum. So this is what we have. So we can actually attempt to do this, without any calculus, because, hey, sum of two numbers is 16. Okay, that's easy. 0 plus 16 is 16. There are two numbers, 0 and 16. The problem is that 0 times 16 is 0. So, okay, let's go one up. 1 plus 15 is also 16. Then 1 times 15 is 15. All right, that's better. Let's try 2 plus 14, because that's also 16. And 2 times 14 is 28. Well, now that's better than 15. Keep going. 3 plus 13 is 16, and then 3 times 13 is 39. It's getting better, right? 4 plus 12 is 16. 4 times 12 is 48. So you get the idea. These values are increasing. That's the product. And as you can see, right, if I go 5 plus 11 is 16, then 5 times 11 is 55. That's even bigger than 48, right? So as I keep going, right, we see that eventually we're going to hit what we want. But, what if this number was not 16? What if the number was 16,784? Like, would you sit there and try all of the combinations? Sure, right? 0 plus 1 or 16,784 is equal to 16,784, and then the product is 0. 1 plus, right? It's gonna take forever. So is there a clever way to deal with this using calculus? And the answer is yeah, and it's called optimization. So what we do is we read the problem and we translate that problem from English into mathematics, which is equations. Sum of two numbers is 16. All right, that's not gonna take more than 2 brain cells to convert. Sum of two numbers is 16. Awesome, done. Right? It's actually 3 brain cells, X, Y, and 16. Right. How about 5, because we have the addition and equals. 5 brain cells. There we go. Now, the other one says, find the numbers such that their product is maximum. Okay, product is maximum. Well, that's easy as well. There we go. So we converted words into these equations. And now I have 2 equations here. The top one is called the constraint. And the bottom one is called the objective. Right? The objective is always the one that contains min and max. Remember, your objective is maximum product. Your objective will be minimum cost, right? So you want the minimum cost. So you're going to say, oh, okay, that's my objective. Now, the other one is constraint. You have to have minimum cost with the constraint that these numbers are adding to 16, right? Because without this constraint, I'm just going to make up, 1 million times 100 million, and there you go, maximum, right? And then someone's going to say, no, because I'm going to use 101 and then, million, and then I'm going to get more. Sure. So we have to have a constraint, right? And then you move along. You can also think about, the freedoms within the rule of law. So you are free to interact with people with the constraint you don't kill anyone, right? That's a constraint. So you are free to move around, to talk, to socialize, well, actually now it's prohibited by government to socialize, but in a normal circumstances and normal states, you can socialize, and then you can, right, talk to people, but the constraint is you can't kill them, because if you can kill them, right, if you kill them, then you are going to prison, right? That's the way it goes. So anytime you solve these problems, you will come up with the 2 equations. One is constraint and one is objective. And objective one is always one with the max. From this point on, when you get these 2 equations, every single problem of this book has same steps. Step number 1, solve for any of the variables from your up there. So y equals 16 minus x. You can solve for x if you want to, right? So that's that. And then plug in, which will eliminate the variable y. See, y is 16 minus x equals max. So now you have an equation which is your objective equation, but your objective equation doesn't contain any y anymore. So now when you multiply this out, you have the equation that you can hit with the derivative to figure out what the maximum value is. So we're going to differentiate this and get 16 minus 2x equals 0. Now, I am not setting this equal to 0. The derivative of maximum is 0. So earlier, when we said we want horizontal tangency, so set derivative equal to 0 to find min and max, we don't actually have to do that now. The derivative of maximum is 0, because what is the maximum representing? It's representing the product of 2 numbers. It's representing one of these. And those are all numbers. So I don't care which one of these is the correct answer. When I take derivative of that, it's going to be 0. So that's why derivative of max is 0, derivative of min will be 0. Because those will always represent a number that you are looking for. I'm looking for minimal cost. Minimal cost turned out to be $7. Then derivative of 7, because it's a number, is a 0. I'm looking for maximum profit. $10,000. 10,000, derivative of 10,000 is still 0. So every time you take derivative of min and max, you will get 0. And now you know what happens. X equals 8 when you solve the equation. And then you can plug that here to calculate your y. So y is equal to 16 minus x, also equal to 8. And now you have x equals 8, y equals 8, which would produce maximum product. Well, we are not that far, right? If you want to continue here, you have your 6 plus 10 is equal to 16, 7 plus 9 equals 16, and 8 plus 8 equals 16. Now, the numbers that you get on this side, right, 6 times 10 is 60, going up. Then you have 7 times 9, right, equals to 63. And then finally, 8 times 8 equals to 64. Now, if you are to go and push into 9, then that's going to be 9 plus 7 is a 16. That's your constraint side. And now you see that you're going back now into a 63, right? So you hit your max value. And then as you flip here, right, because you are still constrained to always have 16, this side will immediately start to fall off. So you hit the peak, and then you lose that, start losing the values. So we ended up with x equals 8, y equals 8 as two numbers that would give you a maximum product. Now, these problems, right, have a very wide range of use. Some of it in engineering, right, and a lot of it in finance and business and economics, because of the constant need to understand and work with profit and cost, and constantly wanting to optimize that. Now there are other things, the whole branch of mathematics in operational research, where if you have masters in that, you can go and set up the factory production, and like a lot of jobs obviously in that area when you have production. So companies need that. All right, let's take a look at geometrical problem. Farmer's problem, or farmer's dilemma, as they would say. So what is this farmer trying to do? So farmer has either, right, he's either making vegetables or orchard, right, with fruit, or has cattle or something, right? So farmer needs to fence off the area of maximum area, right? So plot of land and maximum area under constraint to use up all of the fence that the farmer already has. So say that the farmer has 2,000 yard of fence. It's just laying stacked up behind some shed somewhere, right? 2,000 yard of fence. He wants to fence off a rectangular area of, of maximum area. It's a stupid way to say it, but I guess he wants to fence off a rectangular plot of land. How about that? Plot of land, plot of land of maximum area. There we go. Find the dimensions of the plot. So, so what he wants to do, maybe if I move these words a little bit, maybe I can fit. Rectangular plot of land. There we go. Of max area. Okay. All right. So rectangular. Okay, put the rectangle down. We know the rectangle has A and B as sides. And hopefully we understand that the perimeter fence goes on the perimeter of the rectangle. Right? You don't put the fence everywhere inside, so we're not talking about the area there. We're talking about the perimeter because the fence goes around the plot of land. Now, whether we're going to put cows or apples inside, I don't care. It just needs this plot of land with the maximum area. All right, so let's write the equation. The perimeter is 2a plus 2b equals 2000. You can also use x and y if you want, whatever. And he wants maximum area. AB equals max. Divide the top by 2 to make it, to reduce the numbers down to whatever we can. And ta-da! This is the same problem we had before. The same thing, x plus y equals 16, a plus b equals 1000. There's absolutely no difference. Same steps. I mean, the equations eventually will look different, but it's always the same thing. So b equals 1000 minus a. Now take that, stuff it in the objective equation. So that's a times 1000 minus a equals the max area we're looking for. So this is 1000a minus a squared equals the max. And then we are going to hit this with the derivative. Now please be careful, right? Take the derivative in respect to variable you have. So it's ddA derivative this time around. And that's going to be 1000 minus 2a. Again, derivative of maximum is equal to 0. So we're going to have this one, and we are going to have the I just got the delivery. It's not the DiGiorno, by the way. It's the awesome wife with food. Anyway, so our A is equal to 500. When you solve this equation, we have A equals 500. So now we have A, go back into the equation where it gives you a B. So B equals 1000 minus 500, and we get another 500. So dimensions are 500 by 500 yard. Those are our dimensions. And you're going to say, it's a square again. And I say, yeah, because it's actually mathematical rule that the special rectangle called a square, the special rectangle called a square is always the maximum area. But when you start messing with a shape in any way, the answer will no longer be a square. So if you start with a rectangle, A and B, you are going to have a square as the answer. For third-dimensional, if you take a box and try to find maximum volume, you are going to end up with a cube, which is a box that all the sides are the same. Like the dice for you use to play games, right? The six-sided die. Now, how can we change this problem? Well, here's the river. right? I usually like to put a salmon in here, so you know it's the river. See that? There's salmon right there. And once the student said that's not salmon, those are carrots. They're not carrots because the carrots have the green top. Okay, these don't have the green top, so obviously they're salmon. All right, so now you are going to have your plot of land right there, and you are not fencing off the back side because the river will provide this. The river will provide this thing in the back. So now I have. We can call them x and y. We don't have to do a and b. X and y is just fine. But see, you are now using fence on only on 3 sides. You still have 2,000 yard of fence available. So we're going to have x plus 2y equal 2,000, and we still have xy to be max because I want the maximum plot. So my equation doesn't have a 2 in front of x anymore because I'm not using the fence in the back. The river will take care of that one for me. So now, once you have the two equations, the rest, guys, is just always the same. X equals 2,000 minus, I want to go orange. X equals 2,000 minus 2y. Then we stuff that in here. So now that's 2,000 minus 2y times additional y equals max. Multiply through. And hit this with the derivative. D dy. That's 2,000 minus 4y equals 0. 0, 0, 0. Derivative max is 0. And y equals 500. Take that into equation for x. X equals 2,000 minus 2 times 500 equals 1,000. So there's your 1,000 by 500 yard dimensions now, because we do not have a standard rectangle, right? We messed with it a little bit, and because we did that, right, it's no longer a square for the answer. Now we have 1,000 times 500 yard as the dimension. We have all possible ways to mess with this. Put a couple of bins, right? So you can have your separate animals or whatever, right, go into those bins. So in this case, it's 2x plus 4y equals to 2,000, and it's still xy is max because you want maximum area. You can have the river. I mean, you can come up with literally anything. Put this against the river and then put, I don't know, one of these in there. So now you have 3 y's and a single x. So x plus 3y equals 2,000 yard of fence. And I'm still going for xy equals max. This is another one that I usually show. Again, so let's say you need a little area inside the area. Your job is to just come up with all of the geometry of these black lines, because these black lines are where the fence goes. And each one of these black lines is the length that is taken out of 2000. So if the big length here is x and a big length over here is y, and the small ones are y over 2 and x over 2, let's say it's just whole half of the field, well, I have 2x plus 2y, that's the outer box, and then plus on the inside I have x over 2 plus y over 2, and all of that is 2000. And your x times y is still a max. Every single one of these problems is solved the same way. Once you figure out geometry, you have your constraint and you have your objective function, solve for either x or a y, plug it into the other equation, get the derivative, and you're done. Every problem is the same. Now, that doesn't mean that every problem is easy to make those equations, which is why, right, some students graduate and become engineers and others graduate and do not become engineers, right? There's a difference in understanding how to switch physical reality into mathematical equations so that you are actually useful in the field of design. So one of these problems would be, we can do volume problems, we can do a whole bunch, but there is this really cool problem where I'm trying to find it in the homework. Oh, there it is. The flower garden, optimal garden. So they give you this garden, and they give you, right, the part where the flowers go and the walkway around. So they tell you this is 2 meters, this is 1 meter, same on top and the bottom, right? So this is also 1 meter and this is 2 meters over here. So they give you that, and they say that the garden with an area of 30 meters squared is surrounded by the grass border, 1 meter wide on two sides and 2 meter wide on the other two sides. What dimensions of the garden will minimize the combined area of the garden and borders? So we are looking for dimensions so that total area is minimum. Now, this is the definition of a garbage applied problem. No one ever computes this. Because why would you? It's artistic domain. Just let it be, right? Don't involve calculus, right? Make it beautiful, walk away. However, if I switch this problem into you having a backyard and you are making a pool, and this ring around is going to be a concrete that you are going to pour around your pool so kids can run and scrape their knees, right? Then all of a sudden, minimizing the total surface area in there while keeping your pool 30 meters squared, which is what you wanted the size of a pool to be, you are minimizing the cost of the concrete. Because if you have to pour less concrete, that means it's not just less material, but it's also less of the hours that the workers are going to be. It's going to be dry faster and all of that stuff, right? So the cost goes down if you have the least amount of concrete poured around the pool. So you want to minimize the dimensions, you want to minimize the area, you want to find the dimensions that will minimize that area. And that is something that you can actually save money with if you own a house and you are dealing with these things, right? So now, there might be someone computing this or not. You can just eye it. Obviously, you are not guaranteed to hit the absolute saving minimum. Now, the companies, they're not going to do that way. The company wants to know down to a penny for everything, which we'll see in the next problem. So, what do we do here? Well, I don't know what are my x and a y in the middle for where the pool is or the flower garden, whatever. But that gives me constraint because I know that the area of that rectangle in the middle maybe works out to be a square, I don't know. But that rectangle in the middle is going to have x times y equal to 30. Now, if this length here is x, how much is this length all the way on the bottom?
Square.
Think about the length, right?
X plus 4.
X plus 4, perfect. X plus 4. X plus 4, because you have the same length x, and then you're adding 2 meters on each side, so the total is x plus 4. Similarly for y, is going to be y plus 2. And that area is the total area which we want to be a minimum. So we have figured out the two equations. Guys, the rest is a joke, right? What I need to do is to always have same steps. Solve for any of the two variables on the top. So let's say y is 30 divided by x. And then you are going to stuff that into this equation here. We're going to have x plus 4 times 30 over x plus 2 equals the minimum. So I replaced y with 30 over x. That's all I did. Now, FOIL, derivative, and victory. So x times 30 over x and x cancel, that's just 30, plus 2x, plus 120 over x, plus 8, equals the minimum. I'm not going to bother simplifying or anything because when I hit the derivative, 30 plus 8 is going to, right, go, both of those are going to go. So d dx, there we go. And what I have is 2 minus 120 over x squared is equal to 0. So that's my derivative. The derivative of 30 is 0. The derivative at the end at 8 is 0. So I have derivative of 2x is 2, and the other one over there, 120 over x. Just solve this. It's a basic equation. 2 equals 120 over x squared, which is 2x squared equals 120, x squared equals 60, and from there, x equals plus minus square root of 60. Well, x is length, right? So we're not going to deal with the minus. Now, what are the factors of 60? So we can, come up with the best solution over here. So 60 can be divided by 4, and then we get the 15 over here, right? So it is 2 root 15 is the length in meters for x. And then you can plug that in the equation 30 over this, which is 15 over root 15. Then you hit both sides with the root 15 to rationalize it. Oops. And we get that y is equal to root 15. So dimensions of the pool are, I mean, these are terrible numbers for the pool, but whatever. 2 square root 15 by root 15. Root 50, actually, yeah, they're terrible dimensions for this, because root 15 is close to root 16. Root 16 is 4. So this pool is about, it's wide. I mean, it's actually, it's not a swimming pool, but you can go in and you can splash around, because this is almost 4 meters by 8 meters, which is what? About 12 feet by 24 feet. Something like that. Not too big, not too small. Definitely small side. But then, now that you have your x and a y, you can plug them in your equation to figure out what is that minimum area for everything. And if you subtract 30 from that, it's going to be the area on which you're putting the concrete. Because when you calculate in this equation, when you use your x and y, which are those root 15s, when you plug those in and you compute everything, you will come up with the area of the whole thing. And then you subtract the area of the pool, so minus 30, it will give you the area that needs to be covered with concrete. So it says it's a jacuzzi, 12 by 24 feet jacuzzi. It's like, okay, fine. Nice. All right. Now, time for us to talk some business. We haven't talked business. So now I'm going to pretend to be a packaging engineer and design box for, to ship something. So let's go and say a box with a square base must have volume of, let's say, I don't know, 38 square feet. No, cube. Oh my God, cube, volume. So 38 cubic feet cube. Find the dimensions so that surface area is minimum. Now, can anyone tell me why do we want to minimize the surface area of the box while making sure that it always remains 38 feet cubed?
And then you'd have to create less box material.
Exactly. It's a cost effect yes, so less box material, right, means that you are going to use less cardboard to make the box. Now, as much as you don't care about saving 5 cents for a box, the company does care. Why would company care about saving 5 cents?
Because they have to make millions.
Exactly. Very good. So if you are to own a business or something, now you just proven that you understand how this dynamic works, right? You can't go, oh, I don't care about 5 cents. You are making a million boxes. Right? 5 cents for $1,000,000 is a lot of money, right? So go ahead. 1,000,000 times 5. Sorry, point oh five, right? So that's a lot of money. You save a lot of money if you're able to if your engineer is able to design a box that will cut the cost for that box. All right, let's take a look at the calculation. Uh, we have our box here with so this is the box, and this box has square base, and it will have whatever the height. Now volume is given by looking at this x times y, which is x squared y, and that has to be pinned at 38. There's your constraint. Now minimum surface area. Surface area of the box is, you have a top and a bottom, so 2x squares. The square on the bottom is x times x. The square on the top is also x times x. So you have 2x squares for top and the bottom. And you have 4 xy sides. Each side measures in area x times y. And you want that to be minimum. Now the numbers over here are going to be terrible decimals, right? But that's okay. We can do this. You take your equation, you solve it for y, which is going to be 38 over x squared, and you stuff that in this. It's always the same steps, right? Just pick one variable to solve for. Now you're solving for y because it's easy. You don't want to solve for x and get the square root and all of that stuff. I mean, if you like pain, go ahead. You'll get the same answer. It's just good luck with calculations. Now you stuff this in the other one. That's 2x squared plus 4 times x times 38 over x squared equals minimum. So all I did is I replaced y where it should go. And there you have it. Right? I have now 2x 2x squared, so all of these things, that's good, that's good, that's good. Yes, 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 yes. Okay, so now we just simplify. I am going to, well, that's 2x squared plus 4 times 38. I'm actually not going to multiply that, and I'll show you why. And then one of these x's cancels. Now, guys, if I divide everywhere by 2, I'll have x squared plus 2 times 38, which is 76, over x equals minimum divided by 2, but who cares, when you take the derivative of it, it's going to be 0 anyway. So, whatever. Take the derivative, get your 2x minus 76 over x squared equals to the 0. All right, if the minimum is, I don't know, 30 divided by 2 is 15, and the derivative of 15 is still 0. So we have a 2x equals 76 over x squared, 2x cubed equals 76, x cubed equals 2, 76 divided by 2 is 38, and now you take a cube root, so x equals cube root of 38. Now if you really enjoy your decimals and you can't live without those, I will make you happy. I'm going to calculate this. So math, cube root is 4, so 38, it's 3.36. I think we use feet, right? So 3.36 feet. And now you take that number and you bring it all the way back into a y. So y is 38 divided by 3.36, and that's going to be the height for your box. So 38 divided by, I'll just do second answer, to get 11.3, about. So the dimensions are, let's call this 3.4. 3.4 by 3.4, because the square base, times 11, 3 on the height. All of that in feet, obviously. That's a big box. That's what happened when you just, just put a random number of 38. But when you multiply these numbers, you should get 38. And that's that. I guess we could do one more. Again, all of these problems depend on your ability to... Something is terribly wrong here. Because I saw that this is not working out. Oh, it's x squared. So, okay, 38 divided by 3.36 squared. It's 3.3. Okay, good. So also it's about 3.4. There we go. And 3.4 cubed is about 38. 39 point, yeah, I rounded all three numbers. All right, cool. We got it. Now, why did we get the cube? Because, again, that's a special one, remember? Special one, and it was just a box. There was nothing special going on with the box, and, when you have these very special, when you have just a basic shape, then the special case is usually the solution. Now, we can mess with this box. We can say a box with no top. That immediately messes up your calculations. No top means it's just x squared for the bottom. Propagates through the problem, and you no longer have a cube. Right? Your answers are no longer the same values. We can add the cost and say that the bottom of the box is going to be produced at whatever, right, thicker cardboard that costs more, and then the other 5 sides will have lesser cardboard thickness and quality, and in that case that offsets the equations again. So you just have to be really careful and work very hard on figuring out what the correct equations are. The procedure of solving these problems is always the same. It's a joke. Can take a look at another problem. We did one of the volume. My favorite problem to work on this, it literally takes forever because I use real, not real, but I use the numbers that make sense. So I don't want to go to that one because we have to go into a review for the upcoming exam. But we can still take a look at, some other homework problem. Closest point on a curve. So these problems, they sound really like, yeah, whatever, who cares? But it's not, whatever, who cares? Because this could be, they're minimizing the distance, right? So what's the shortest way to go from point A to point B on a flat surface? And this applies. So what point on the parabola y equals 1 minus x squared is closest to 0.11. So what is the situation here? If you draw this problem, we're going to have a parabola at 1 that opens downward. And then there is a 0.11 over here. They're trying to find the point on the parabola that is closest to the 1, 1. So clearly not 0, 0. Clearly not this one. Clearly not that one. Right? It's some unknown point here. And we call that point xy because it lives on the parabola. Okay. So, yay, I already have the constraint. Constraint is that the point has to be on the parabola. So the only thing is, what I need is a formula that will connect these two. Does anyone know what that formula might be? What am I trying to minimize here? Come on, guys, what I'm minimizing? Not asking for the formula, asking for the concept. What am I minimizing? Am I minimizing volume?
You're minimizing distance?
Thank you. I'm minimizing distance between 2 points. Therefore, common sense should be use the distance formula. Distance formula D is the square root of x2 minus x1 squared plus y2 minus y1 squared. So this is the basic formula from algebra course, which is the distance formula, and we want that to be minimum. I also have that y is equal to 1 minus x squared. Now, I'm going to rewrite this distance formula as the square root of, and now we can call, one of these points 1, 1, and the other one is xy. So we can go and say x minus 1 squared plus y minus 1 squared equals the minimum, and I also have y equals 1 minus x squared. So I'll go like this. Which color? Purple. 1 point is 1, 1. The other point is unknown xy, which is why we have x and a y there. So one set, it doesn't matter which one is which. This is all commutative, right? So you can pick any point to be your point, first point, and any other point to be the other point, whatever. So that's what we have. Yeah, all I need to do is some algebra and that's it. So we already saw, this is already solved. It's nothing to do there. All I need to do is to take this and stuff it inside the y, and we're done. I mean the derivative and all that stuff, but we're done with modeling. So square root of x minus 1 squared plus, and instead of y, 1 minus x squared minus 1 squared equals to minimum. So here's my y minus 1 that used to be y minus 1, and now it's just 1 minus x squared minus 1. Now 1 minus 1 is 0, and then this negative in front of x squared will be killed by this square anyway, so we might not worry about it as well, right? So we have x squared minus 2x plus 1 when you FOIL the first parenthesis, and on the second parenthesis you just get x to the fourth. And all of this is equal to a minimum. And now we differentiate and solve for x. We better get, some x that it's small, because we can see on the picture we drew that, right, all of your lengths have to fit in this 1 by 1 square, so all of the lengths inside, even though this is diagonal but it doesn't go all the way through, right, the lengths inside should be less than 1. I mean, it's bounded by root 2, which is 1.4 roughly, so all of the lengths inside absolutely must be less than that, because that's the diagonal, the longest you can draw inside. Anyway, hit this with the derivative. And here we go. The derivative of the square root is 1 over 2 times the same square root. Now I'm going to put this in decreasing order of powers. And remember, I have to put its derivative on top. So 4x cubed plus 2x minus 2 equals a big fat 0. So now you cross multiply, that completely kills the denominator, and you just have this. Cross multiply, and you get the one on the bottom. So now,
Professor,
yes.
did you use logarithmic differentiation to get that?
No, I just used the basic formula. Square root of x has a derivative of 1 over 2 root x. Right? And you can see that that's the form, but I use the chain rule to deal with the chain rule of the bottom to deal and put it up there. So that was the, yeah. Cool. Now I'm not going to waste my time and factor this, because polynomials are the nastiest over here. So I'm just going to go and say factor 4x cubed plus 2x. I'm cheating on the computer because I don't want to sit here forever. Oh, I didn't want to say factor, I wanted to say solve. Solve for x equal to 0. There we go. That's what I need. And approximate forms. What are my decimals? There we go. So we have 4 solutions. 3 solutions. And one of them is real. The others are complex. So 5, 8, 9, 7, 5, which I'm just going to round to about 0.6, because, right, this 9 will make 8 into a 9, and then it's just very close to 0.6. And I can find the y by squaring this. So y equals 1 minus 0.6 squared. That's going to be 36, so 0.64, and about. So the point xy is about 0.6 and 0.64. And that's it. There's the point that it's closest to that the thing. All right, so now a lot of problems, right, for you to enjoy. And if you are feeling, right, that you know this really, really well, then try problem 63. And yeah, good luck. 63 is awesome. It's another Ferris wheel problem that I mentioned before, and it has a lot of good insight into all of this. All right, we will review this next class, which is on Monday next week. Now we're going to take a break. When we come back, I hope you will have questions ready for the review portion of our class today.
Professor?
Yes.
I might